My name is Kieran Kavanagh, and I'm a Senior Solutions Architect at Amazon Web Services. I'm here with my customer, Fei Yuan, and my colleague, Kunal Batra. And today we're going to be talking about implementing machine learning workloads at scale on AWS. Now, it's really interesting to see that just a few short years ago, one of the main discussions in the industry was all about how to use ML to differentiate your business in some way. And now we've very rapidly progressed to a point where pretty much everybody's using ML. And now it's all about how efficiently you're doing it. Companies really want to automate the entire process as much as possible. Within Amazon Web Services, I work on a solutions architecture team that covers all of Amazon. And focusing on ML in that team, I get to work with lots of different organizations throughout Amazon who are using ML in different ways, working on interesting ML workloads. And today, you're going to hear how Fei's organization is implementing ML at scale on AWS for workloads that are absolutely critical to Amazon's business. Fei, would you like to provide more details?
Thank you, Kieran. By showing your hands, how many of you have bought something on Cyber Monday? That's great. So you still be able to do that while you're at reInvent, right? If you notice when you check out on Amazon.com, you pay your shopping cart with credit cards, with gift cards, reward points, or if it's a large purchase, you divide it into multiple installments, and then maybe you have corporate customers over here paying by invoices using a line of credit. You have used the system that I and my teams have built. So my name is Fei Yuan. I'm a senior engineer from consumer payments in Amazon. We own one of the largest payments and transaction network in the world, handling hundreds of billions of dollars every year, and then billions of transactions every day. So let me ask you another question. How many of you have deployed a machine learning model in your production system? That's quite a lot, probably 50% or 60%. So how was the experience? Did you feel during this process of working with your data engineers, data scientists, software engineers, training a model, getting the data ready, approving it, copying to the production line, and then monitoring that and iterating it, this whole process, was it easy or there was challenges involved? And then to us, in consumer payments, we have hundreds of models to manage, a lot of iterations with many teams, and it has become a really significant challenge to us to do that. So today, I'm not here to talk about machine learning algorithms or interesting way or SageMaker functions, features. I'm here to talk about how do you manage this process so you can have something sustainable in your organization. So one of the questions that we usually discuss with our teams is about where is the hard part, or why is the process of doing machine learning development process so special, and why does it matter? So the part making it matter is comparing to traditional programming and machine learning programming is that with traditional computer programming, you write a code, you know the behavior. You write some unit tests, you write some integration tests, and then you probably have some pre-production tests as well. So you know exactly what you will do in the production system. But with machine learning, this is undeterministic, it's unknown. It's unknown behavior driven by data and model. So you can say that I'm doing it for once and it's doing well, but then because of the unknown part, if you don't have something that makes it sustainable, it's very dangerous. There's a high risk at stake. And you could potentially lose billions of dollars or millions of customers. So the hard part of ML is really about how do you make this process a solid process so you can iterate on that and have multiple versions, multiple models in your production systems. As an engineer myself, let me just talk about a typical day in Amazon as I work. So the first thing we do is in the morning, we open our favorite IDE, for example, in this case, IntelliJ or Eclipse. We write some code, and then once we feel good about it, we run git commit, then run another command to send it to to a code review system. When we send it there, I forgot the part about unit tests. So you need to write a unit test to cover your code. And usually we're looking at least the ratio of 2 to 1. You write 2 unit tests per functional, per unit, per code logic that you develop. One is happy pass, one is sad pass. You submit the code to your peer, and your peer look at, they're automatically notified by email, or you just go there and tell them, please look at my code. They release some comments, more iterations, And then when you are feeling good about it, you run git push, which will trigger an automatic deployment to a previous configured code pipeline. And that pipeline has multiple stages. So one of the stages is beta testing. The QAs or engineers put out automation integration tests there that will go through. When that passes through, then there could be another stage. I'm going to skip those details. It will go into production. Once it goes into production, then the pipeline will be able to monitor if the hosts are working or not, and if there's any downtime, there's a healthy check. And if something goes wrong, it will automatically roll back everything back to the previous version. So to Amazon engineers, probably sitting here or not sitting here, this system has been working amazingly well, supporting thousands of services that we have behind Amazon.com. And the interesting thing is, when we start to look at how do we scale our machine learning development, what is the process that our data scientists, data engineers, and software engineers go through for the machine learning, they're going through a similar process, but they have not realized it. So the part about model development lifecycle is, let's just go through very quickly on what they do. The first is there's data sourcing. Data engineers, data scientists, they work together. They go to some internal Amazon data warehouse, which has millions of data sets, and find something that's useful, run some ETL job. And there's a good practice to do data quality assurance as well, to make sure that data is valid. I'll explain that a little bit more. Feature engineering is about converting your raw data into something that's probably more useful. For example, total number of orders in the last 30 days rather than just the last order amount. And then data scientists go back to write their code or pick an existing machine learning algorithm somewhere out there. They run the training on a laptop, on their desktop, or find an ad hoc EC2 host, train it, and get the result out. And then they talk to client teams who use the machine learning models to say, please copy my model to your system so you can host it somewhere. So there's a going back and forth there. Going to the production integration is the client system usually just has to find a way to take the machine learning, the inference score into their system so that it converts into some business actions. And then obviously there's monitoring back and forth. So this process, if you see that, it's a manual process. Compared to just I mentioned about SDLC, software development lifecycle, it's human-driven. And typically, when the process is human-driven, error-prone, a lot of inefficiencies, and it's hard to even find a versioning or auditing along it. So in Amazon, we usually automate everything as much as we can to invert them into machine-driven process, and only ask for human inputs when it's absolutely necessary. So we are going to go into each of these stages and talk about the lessons we learned, the experience, the problems, technologies we used, and then we'll talk about how we put them all together into a machine learning development lifecycle infrastructure that help us to scale in consumer payments. And just to quickly go over the list of AWS services, I'm sure most of the folks are already familiar with these. S3 to storage artifacts, IAM to control permissions, CloudFormation as an infrastructure as code, SageMaker, there's a lot of functions, lots of features there. Use Step Functions to orchestrate workflows, Lambda to run serverless code. And then the code commit, code pipeline, code build as a continuous pipeline. Okay. So we're going to, as I mentioned, we're going to talk about 8 stages one by one, and I'll cover the 3 stages on the data. The first part is data preparation. As we know that if there's no data, there's no model at all. So the first thing we need to do is to figure out a way to get data ready in the environment. And on this slide, you can see that we are using a hypothetical case to detect whether a purchase is fraud or not. And there are 3 data sets that we have, and using order amount as an input feature, account tenure, how long this customer have this account open, and then the fraud status, whether this particular transaction is fraud or not. So we use 3 data sets and then train them in order to detect inference whether a particular purchase today is fraud or not. The challenges we see in the data sourcing by working with multiple and many data science teams in Amazon is, the first thing is, it's very difficult to find the features, the data that you're looking for, because you may have a large data warehouse, and then the teams putting their data inside, and how do you know which one to use? Maybe there's duplication, and people are calling their columns in a certain way that may not make sense to you. So almost to every team that we see, the first thing they need is to have a curated data store. So regardless whether the organization already has data warehouse or not, it's better to have, in our experience, to have a curated data store. So this data store will handle metadata. You'll say that this particular feature has some information where does it come from. And so in our consumer payments, we build a system that's based on DynamoDB, based on S3, and then store the metadata so that scientists can go there and browse and search and reuse a feature that has been pulled by using ETL from other sources. And the second challenge here is that in the traditional way, most of the features in your data warehouse, they are generated by using some kind of batch or query process. So you look at the original operational database. Operational database in this case are the ones that support your production systems. They run a query there and then capture the results in this data warehouse or data lake. So that not only affects your production system, but also there's a latency. There's a latency of 1 day, 2 days. That's very common in Amazon. So what we learned over the years is that we should usually never generate your data warehouse data from your operational database directly, because that can impact your operational database, the one that's serving customers. There's a lot of traffic there. So what we do is we started to convert ourselves into more streaming-based. And you probably have went to quite a lot of sessions these days about streaming. We've done streaming years ago. So the streaming part is you based on DynamoDB stream records, which is you can think about it as more of a byproduct coming out from your main database. Doesn't affect your current customer load. And then use that to go through another lambda function or something like that, and go into the file host to sync those into micro batches. And then for the micro batches, you have the delta records. Then you run further ETL job to merge them with your original snapshot. So I'm not sure if you guys are familiar with this process. It's about generating a new snapshot based on the changes. And by doing this, we have much more fresher data to use, and it also does not impact the original operational database. So those are two things we have adopted. And then the second stage is about data quality monitoring. So here the case is we have an account tenure originally as stored in the database as number of days. And then at some time, some engineers, they decided to, okay, let me store in number of weeks. Or maybe this is not a good example. You can say that I want to store in number of hours or number of minutes to be more precise. So when that happens, the API that the team is operating, will that cause any problem? No. We're a service-oriented architecture company. So all the APIs, there's a contract, latency, bandwidth, and everything there is guaranteed, and all the teams are interfaced that way. So APIs is fine because they can change their code logic behind the scene. But what's going to happen is it's going to be a terrible thing for all the downstream systems, downstream customers who depend on your data. And this has happened many, many times of anti-patterns reusing the same column, changing the position from double to integer, or changing the true or false into 0, 1. And how many of you have seen this before in your systems? That's right. We have done this again and again as well. And usually we in a design review that I tell engineers, oh, please don't overload your column, have a separate column. And this is a really bad practice because somewhere along the line, you'll impact someone. So the first challenge we have with data quality monitoring is to increase the awareness of it. A lot of times people probably don't care. They don't think it's a problem until something happened. And so increased awareness is very important because if the data is not right, your training and inference will just go wrong. And you can have something that's been running for months without you knowing it. And we've seen cases that the machine learning inference is even worse than random selection. And the second part about data quality monitoring is now you need a system. You should have a system in place that's part of your process, part of your pipeline. If the data is not good, it should not be used to train or to run the inference. So what we developed is we have a system that will subscribe to the events of every time. I remember talking about the first curated data store. Every time there's data that's published, data set published, we will capture that, read that, and parse through, and calculate, for example, number of rows, number of columns, and then for each of the column, look at to a maximum value, or average, or standard deviation, and then compare that with the previous day, previous 7 or 10. So this gives us idea about has the data been drifted or not. If the data is drifted, there's something happened. You probably should just stop the process and have someone look into that as an on-call or some engineers. So we have this system in place for many, many years, and it has saved us billions of dollars. And it's really important to have this type of data quality checks. The third stage is feature engineering. The idea about feature engineering I explained a little bit earlier. Here you can see that if you look at the order amount from 23rd, 24th, 25th, it's not changing too much, $50, $25, $75. But if you look at the total in the last 30 days, then from 24 to 25, something doubled. And this is probably something really simple from our data scientists here. And we're just looking at the total has doubled. And there could be a fraud signal that we should be a feature to the models. The challenge of doing this, of running feature engineering, is a lot of time data scientists just find the easiest way to calculate that. And they could be loading the entire data set in the memory, provision some extremely expensive EC2 hosts out there, and then write a Python code to do it. Or they could do it another way, and it's not easy to manage. So we've seen so many different variations of feature engineering while they're doing a similar work. And the solution for that is we came out with a system that will allow data scientists to be more of a configuration declaration based to say that I want to calculate standard deviation or total of this column. And then behind the scene, it will generate SQL, ETL job, and to compute that. So this is a lot easier than moving those resources into their own model code, which is scrambled together and then coupled to each other. So that's one. And the second is, when you have a large data sets, hundreds of millions of rows, and then you are looking for the last 30 days of total amount, what you will need to do is you have to pull all the 30 days of data sets and compute the total. Every time there's a data set run, data set publish, you have to go back to 30 and compute. And that's very expensive. So computation cost is very high. And in Amazon, obviously, I'm sure in all the companies, every time we look at design, we have to analyze how much it costs us, how much computation, and just find the best way to do it. So to avoid this huge cost of doing aggregation, one of the optimization we have here is to, similar idea as the data quality check, we store some intermediate states of the columns. So if we're looking at the total, we'll be computing the current total amount in the last 7 days. And then as the new data comes in, we will just increment it and on top of that. So this effectively changed the computation complexity from order of n to order of 1. And that's the optimization we do, and it's saving a lot of money by doing this way. So those are the 3 stages that I covered in feature engineering. Next, I will pass it to Kunal on the model development.
Thanks, Faye. Hi, everyone. So my name is Kunal Batra, and I'm a senior technical evangelist here at AWS, and we're going to talk about model development. So after we finish with that feature engineering phase, we now move on to model development, where we need to ask ourselves which type of algorithm we need to train our model. Right? And we can do this by taking a look at the data we have, as well as the complexity of the decision our model needs to make. So you can see on this slide here, you can see supervised learning, unsupervised learning, all the way to reinforcement learning, which are some common algorithms we can choose from. So once we decide which type of algorithm we require, there are a couple of ways where we can implement this. SageMaker comes with over 60 different built-in algorithms we can take advantage of. But if the algorithm requires not part of SageMaker, there's still a couple of other options that we have. The next option is the marketplace. And the marketplace is essentially a digital catalog with listings from other AWS partners and vendors that we can take advantage of. So in the machine learning section, we have over 200 different models and algorithms that we can choose from. But still, if what we're looking for is not part of the built-in algorithms or the marketplace, no fear, we can create our own custom algorithm. And to do that, we can create a custom workflow. So you can see in the slide here the AWS code pipeline, and there's 2 services in there, code commit and code build. So code pipeline is our managed CI/CD service. And Basically, what we can do is just create that algorithms ourselves locally, push that up into code commit. That'll have our code, our dependencies in there, and then you can see it'll trigger AWS Code Build, our managed build service. And that'll go ahead and take a look at the root of our repo, and from there, follow the instructions, and in this case, it'll go ahead and build a Docker container. Once it builds a Docker container, Code Build will then ship that out to the Amazon Elastic Container Registry, which is our service for durably storing those Docker containers. And then from there, it'll go ahead and we can use that in SageMaker for our training process. And Kieran will talk a little bit more about that.
Thanks, Kunal.
Of course.
OK. Now, at this point, we have prepared our data. We have chosen which algorithm we're going to use. And now it's time to finally train some models. We'll start off with our model training job. And there are a number of things that go into this. Of course, there is the actual data set that the model is going to learn from. And also, there's the algorithm that we're going to choose, as Kunal just described. We also have this concept of hyperparameters. Now, these are things that can affect how quickly or efficiently our model will learn, but they're not components of the actual data set that the model is learning from. These can be things like learning rate, number of epochs, et cetera. They vary depending on what kind of algorithm you're using. Our model training process will create some artifacts that we will generally store in S3. And then we can put these together with our algorithm to create an actual model for people to interact with. Now, after we've created our model, we want to test it before we actually decide whether it's well enough for people to interact with it in production. And for that purpose, we will perform some backtesting. And to do that, we will use a holdout data set. This is data that is similar in structure to the data that the model learned from, but it's new data that the model hasn't seen before. And the reason we do this, we want to see how the model is performing. We want to calculate some metrics to measure how the model is performing. Now, let's take a look at some challenges that exist at this point in the workflow for data scientists and data engineers in the industry today. At the beginning of the presentation, Faye asked how many people here had ever deployed models before, and it's good to see that a lot of hands went up because this is an advanced machine learning session, so it's good to see that there's already a lot of base knowledge out there in this process. As you all know, for those of you who have deployed models, you train a model once and then you're done, right? Absolutely not. In fact, what's going to happen is that you're going to work through this process many times, iterating through and changing things here and there. Maybe you're using different versions of your data set. Maybe you're evaluating different algorithms. And you're definitely using different hyperparameter values to see how they affect your outputs. Now, one challenge here can be just keeping track of all of this. If you're doing a lot of experimentation to find the best version of your model, you're tweaking different inputs and measuring how they affect the outputs. And how do you track all of that? People have been doing it manually in spreadsheets. People have been writing kind of custom code to try to capture some of this stuff. But that really gets difficult at very large scale. Amazon Consumer Payments has hundreds of models. And in each case, they may be performing lots of experiments to find the best version of each model every time. So doing that at scale and trying to track it manually can be very difficult. There's a couple of things that I should mention from this week that you should be aware about. One is that for tracking all of these things, SageMaker has just announced SageMaker experiments, and that will help you with some of that, some of those activities. And then also, when it comes to automating this process, because we talked about automation is really important when you're doing this stuff at scale, there's something that SageMaker has announced called Autopilot, which will help to automate some of this. And then for the hyperparameter part, there was already hyperparameter tuning jobs there, which in using that, you can use Bayesian optimization to help accelerate the hyperparameter tuning process. Now that we have our models trained, we want to deploy them so that people can interact with them. We'll start with our model from the previous step, of course. And there's generally two different ways that we can deploy our model. One is in batch inference mode. In this case, you'll either run it manually or perhaps periodically. And when you run a batch inference job, it will go and take whatever data set you've specified, process through all of that, and then create an output data set, which are the inferences it has made from all that data. And that's what your clients will interact with. So your clients will come and read that data from the data set that has been created whenever they need that information. And an example of this is, let's say if you're making recommendations, things that people may want to purchase based on stuff that they've purchased in the past, for example. The historical data, you don't need to process that every time in real time, right? So that you can do that offline most of the time. Another use case is for online inference. This is where clients need to make inference on new data that has come in. You have not had any opportunity to process it offline beforehand. And for this case, we need to create some kind of endpoint for the clients to interact with. And then when clients need to get an inference from your model, they will go ahead and call that endpoint. An example in this use case may be, as Faye mentioned earlier, fraud detection. In this case, you have a transaction that's happening in real time, and you want to assess whether that transaction looks legitimate or whether it may be questionable based on the features of that transaction itself. So in this case, it's happening in real time. The client service that's calling that endpoint needs to get an inference on new data right away. Now, what are some challenges that exist here? Well, one can be just deciding which use case to implement. And initially, this actually seems really straightforward. Surely you know whether your use case is online or offline, right? And in some cases, that is the case. So basically, I talked about earlier, whereby the two examples I just gave, they're pretty clear examples of each use case. But when you start dealing with really large scale and really large data sets, you need to take some other things into account. For example, Amazon Consumer Payments has billions of rows of data that they could process through. And if your clients actually only need a subset of that data, then it would not be efficient for you to process all of that data and then only a small subset gets used. In that use case, you may actually want to implement an online scenario. But one thing that you need to keep in mind here are the SLAs of your client services that are calling and how quickly they need access to that data. Because in the batch inference use case, they will be simply reading from a data set. And performing a read operation on a data set looking for, let's say, a key value pair is pretty much always going to be quicker than computing inferences in real time, no matter how much you optimize your online use case. Now our models are trained, they're deployed, our clients are getting inferences from them, so our jobs are done, right? Not quite. Even after we deploy our models, we're going to have to monitor them. We're going to have to keep ensuring that they are behaving the way we expect them to. And if we take an example from a supervised learning use case, we will generally have 3 data sets that we would use for this purpose. We have our input data set. They are the data that we're going to feed into our model for inferencing. We have our output data set. They are, of course, the inferences. And then we have our ground truth label data set. So these are the known correct answers. This is what the model should have guessed. And with these 3 items, we can put them together to calculate some metrics about how accurately did our model perform. Whatever it guessed at, was that close enough to what it should have guessed? And when we mention closed loop and open loop on this slide, what we mean is that with the closed loop, at this point, we can just generate a report, and somebody comes and reads that at some point. Maybe somebody comes in the morning, and they read the report that was generated last night. And then they decide, OK, the model is performing as we expect, or maybe we need to do something to update it. But with the open loop, what we're doing is we're monitoring those output data sets as they're being created in real time. And then we can proactively do something right away if we find that the model has drifted outside certain parameters that we've specified. And in that case, we can generate alarms. We can send an email to somebody. And there's something else that we can do at this point that I'm not going to mention yet because it's our big reveal later in the presentation. But just notice that at this stage, we can do something proactively to update our models. The final stage in the MDLC, then, is how clients actually interact with our models. And how this happens is that your clients will be collecting features in real time, and then we have this decision point that we talked about, whether it's online or offline. In the offline use case, it's simply going to come and read from a data set that was prepared beforehand. But with the online use case, it's going to go ahead and call that endpoint that we talked about creating. And in either case, when you get an inference back from your model, most likely you don't want to just go ahead and trust whatever the model says. You're going to need to perform some kind of validation. You're going to run some business rules, and then based on that, you'll take actions. And to give an example for Amazon Consumer Payments, they have, of course, regulatory requirements that they need to comply with, and they need to check when, OK, after we get an inference from our model, what is the next step? And is that in alignment with our compliance requirements before taking action? Just to mention some tools that we've been using in some of these previous steps. For the collecting features, we're using Amazon DynamoDB, and then for inference, using SageMaker. And for running the business rules and performing actions based on those rules, because this is an event-based workflow happening here where new data has come in, we've received an inference from our model, and then we're going to do something based on that, well, Amazon, our AWS Lambda is a good fit for that use case. Now, in the past few stages, we've gone deep into each stage, and we've covered a lot of technical details. And now Faye is going to bring it all together for us.
Let's bring it together. So Kieran and Kunal has talked about all the stages, individual stages, and you're probably still wondering, they're still disconnected from each other. So the challenge we have, even after working through each individual stage with our data science, software engineers, and come up with those solutions that we just mentioned, manual process, very inefficient, and we still have all these challenges that we need to solve. So the first solution that we looked at across teams is just ignore it. And thank you, Kieran, for pulling that picture, and it's probably not as bad as it looks. But it's a valid solution, too. Not saying it's just not good. There's many teams in Amazon, we start something from being scrappy and making sure that it works, this is what customer wants, and then iterate on that. So having that without upfront investment is good when you have one model or just doing once. But the moment you need to iterate more, then that's where the challenge comes. And then some of the teams in Amazon, they have been building heavy lifting, big machine learning pipeline by running Python code, running library, and then going back and forth, entire system that a two-piece team will take years to build. Is that feasible for every team, every organization in Amazon to do machine learning? Obviously not. And a lot of times, those systems, they are not multi-tenant. They are not meant for everyone to onboard. So many teams choose to ignore it, which there's a high risk. And then the solution that we're presenting here is, instead of thinking about, OK, we need to put some platform out there, SageMaker has been, since 2 years ago when it released, when it announced in reInvent, it has been very powerful. And then there's the Step Functions. How many of you here have used workflow and Step Functions? OK, that's good. And Monday, Tuesday, I did a builder session with people who were sitting on the booth, and they didn't use Step Functions before. So we spent 1 hour to teach them the syntax. If you're familiar with the idea about finite state machine, it's really easy. The syntax is about, I have this state, I have this step. What should I go to the next one? Which one should I go? Where's the condition? So they were able to learn it in 1 hour and made the entire MDLC workflow work. So the idea here is that instead of building a configuration system, a system by configuration, we're looking at a system by convention. We can use a workflow to stitch together different AWS services, SageMaker components together into workflows to give you those MDLC workflows. So in consumer payments, we have developed a couple of templates, or you can call them blueprints, templates. For training, in the training, you may be pulling data from somewhere, train the model, store the result somewhere, and then automatically pipe that to an API gateway or to an email for someone to look at the result and please approve it. And if that's approved, then the next step on the workflow is to store it in DynamoDB. And from there, you continue. Batch inference, similar. Real-time inference is how to get all the way from a model, from a source code, to a SageMaker endpoint. So all these templates we have, they allow customers to quickly put into their system without going to do a heavy lifting development. The basic architecture of the MDLC workflow, there are 3 layers. On the bottom layer, you use SageMaker, batch for some data computation or glue, ECS, EMR. And then in the middle layer, those are Lambda functions. Lambda functions, a platform team in consumer payments will be writing those Lambda functions as an adapter. So each one is a very lightweight method, a function to say, I want to kick off this job, or I want to get a result. And you're probably wondering about there's difference between synchronous calls and asynchronous calls, because some of the work with, for example, SageMaker to run a batch transformer will take a long time. It could take days, or sometimes we see it taking weeks. So Lambda is probably not the best choice here. There are 2 solutions. One is you can write your own start and check the status in a loop, which is a typical process flow will look like. And the second is there's a lot of integration these days between Step Functions team and SageMaker team to make a certain call, a certain functionality in SageMaker synchronous. So they have something as ARM to just call the SageMaker, please run this transform job. And it will only continue in the workflow until it's finished. So that's very convenient. And then once you have this library as each individual building blocks, you can look at them as your component. And then on the yellow, the top level, then you construct each individual step functions and put them into CloudFormation. So those are the templates that we are talking about. So next, I'll pass on to Kieran to show you 2 examples.
Thank you, Fei. Up until now, we've been talking mostly about the concepts involved in all of this process. So how is all of this actually built on AWS then? At the beginning of the presentation, I mentioned that automation is really the key, right? When you're doing this stuff at scale, you have to be automating it as much as possible. So what you're going to see here are these multiple layers of recursive automation whereby we're automating one thing and then that automates something else, and that's how it kind of bootstraps itself. We begin with CloudFormation, and that's going to automate the creation of our infrastructure that's going to run our workloads. And even our CloudFormation deployment and any updates to our CloudFormation, even all of that is automated via code pipeline. Earlier in the presentation, Kunal mentioned about code pipeline to set up a CI/CD process. And because CloudFormation is infrastructure as code, you can set up a CI/CD process for your CloudFormation. Now, what will our CloudFormation do? It's going to automate the creation of 2 workflows. The first one it's creating is an AWS Step Functions state machine that will automate our training workflow. In this case, we start off with our training job. Going back to our conceptual slides, this is where we were taking our algorithm and our data set and our hyperparameters and putting them all together. Now, as we're training our model, we want to be able to approve it before promoting it to production. And again, we want to automate that as much as possible. In some cases, depending on the complexity, it'll be difficult to completely automate it, so you may need to email the results to somebody for them to come and look at it, and then there could be an embedded link in that email where they can just go ahead and click on it to approve that workflow and promote it to production. But in some cases, if you have a pretty simple model and you know that, okay, we expect the outputs from this model to be in certain ranges, then you can automate that. You can check, is it within this range? If it is, then go ahead and promote it. And when we promote it, then we invoke our create model API. And what happens at this point, when the model gets created, we will store the details of that model in DynamoDB, and you'll see why that's important in a little while. We'll store the Amazon resource name, which is a unique identifier for that model, in DynamoDB. The other thing that our CloudFormation is going to do, it will automate our batch inference workflow. And in this use case, it's again an AWS Step Functions state machine. And we talked about with batch inference, you can either invoke it manually or you can do it periodically. And in this case, we're using Amazon CloudWatch event rules to automate running this periodically. So you can run it every day, every month, whatever is most suitable for your use case. And then when we run that batch inference job, it will refer to the model that was created in the training workflow. And how does it do this? Well, it looks in DynamoDB to see the details that we stored when we created that model. So that's how that link happens there between these 2 workflows. Now at this point, we run our inference. I mentioned that we want to monitor our model, how it's performing, even after it's in production. And I said that at this point, we can do something proactive. We can send an email to somebody. And there's something else we can do, which is the big reveal. And that is, we can go ahead and actually automate the retraining job. So we find that our model has drifted somehow, then we can automate retraining it, let's say on a new version of the data set, to bring it up to the latest data version. Like maybe your model was trained a month ago and it's been doing fine for a month. Every day you're monitoring it and it's doing great. And then after about a month, you found that it drifted. So you want to retrain it on an updated version of the model. And now at this point, it's a completely autonomous self-healing system. So it's kind of like perpetual motion. But basically, at this point, you don't need humans in the loop anymore for most of the use cases. Where you may want the human to step in is that if you find that you've retrained your model, let's say 5 times, and it's still not at the accuracy you expect, well, at that point, maybe there's no point in just keep looping through it, and then you flag it for human interaction. But again, when you're dealing with scale like Amazon Consumer Payments, whereby they have hundreds of models, they don't want to be manually curating these models every day and seeing how they're doing and et cetera, right? So for the most part, these models are just functioning away by themselves, retraining whenever needed, and then every now and then one of them flags and says, I need help. Some human needs to come in here and get involved. Just one other announcement that happened this week, in case you missed it, was that SageMaker has now announced SageMaker Monitor modeling, or model monitoring, and you can use that to make this process easier. Now, this is the architecture of how it all works. Let's take a look under the covers and see what's happening behind the scenes and how these workflows are actually implemented. These are the 2 step function state machines. These are actual screenshots from the AWS console. And if you understand Amazon State Language, or ASL, then you can actually build these by looking at the states here. And we just talked about the offline workflow, and we mentioned that there's 2 ways of deploying our models. We also have the online use case. For the online use case, we will start off the same way, where we have CloudFormation being automated via code pipeline, and that will automate the creation of our state machine to automate our training workflow. CloudFormation will also create our inferencing workflow, but in this case, it's a little bit different how it interacts. Previously, you saw that we had CloudWatch event rules kicking off our batch inference jobs periodically. In this case, we have a live endpoint that we've created, and that's what our clients are interacting with in real time. So every time your client invokes this endpoint to get an inference from your model, again, we have that mapping going on. This is how the endpoint knows which model to use for this request. And then again, from this point onwards, we're back to the usual use case, whereby we're monitoring every inference that comes from that endpoint, and then we can retrain if needed. One clarification to make here is that generally, if you have, let's say, thousands of transactions going on, and one inference is not where you expect it to be, you're not going to kick off a retraining for every inference that is not within the bounds that you expect. Basically, we've simplified it here a little bit. What you're going to need to do is you're going to have a little bit more orchestration going on, whereby you're measuring all of your models and all of the inferences and seeing overall how are they performing. Generally, there'll be some percentage that you can find tolerable. And if you find that their inferences in general are below that tolerable threshold, then you can go ahead and retrain your model again. And here's a state machine for this use case. Here you can see that the inference use case is a bit more complex here, and that's because we're creating that model in real time. And we have a wait loop in the middle here, whereby we're waiting for the endpoint to come up, et cetera, before proceeding. But again, this is the actual state machine that is being used for this workflow. Now again, we kind of went a bit deep into everything here. Again, I'm going to hand over to Faye one more time to summarize.
Thank you, Kieran.
Thanks.
Okay. You saw the workflows that Kieran just showed you. Do you have confidence that you can build it in a week or 2 weeks? It's not difficult. It's just quite straightforward if you look at all the steps and integration. And we were able to deploy one pipeline for one team just within 2 weeks, and that was able to help us to scale very, very quickly. There are many, many teams in consumer payments, and this was something that we adopted, and also outside of consumer payments. To recap the model development lifecycle, we talked about 8 stages. Data sourcing, remember, curated data store, looking into streaming-based data instead of just going to operational database. Data quality assurance is very important, and I encourage you to see if you can put some system in place to do that. Model development, make use of a SageMaker algorithms, and we start to convert ourselves from an original approach to SageMaker because it's container-based. All the dependencies are all packaged together. You can write your own code and still have the same container running on your desktop and also running on SageMaker environment without differences there. Feature engineering is another one. You can look into incremental feature engineering to reduce computational cost. Model training evaluation, make sure that the model that's trained, you can always go back and see how it was trained. We have examples that certain models are not working well, and after a year, when people wanted to figure out how was it trained and who wrote it, and no one knows because it was just not tracked. So this is very important to make sure, and the evaluation, make that part of the process so someone will see the result and get an email, or you build a dashboard instead of people, data scientists, printing them out and review with paper. Deployment and inference, we talked about batch and online. There's different consideration on which one to use. And then the production integration, usually we go with data collection, model inference, business rules, and convert that into actions, 4 steps, and then monitoring as well. So the benefits we saw in this solution, and this is the last slide to show you part of the summary of the benefits. The first thing is, by using workflow to connecting together, it's very rapid, it's very fast. It allows you to bootstrap instead of building another abstraction on the top of everything. So think about connecting the service that AWS provides you rather than building something that's on top of it. And the second part is by leveraging SageMaker. You probably saw a lot of sessions around SageMaker. It's not overlapping the component that they produce. So you still benefit from all the features, the scale of the data processing by doing this way. And then the third part is continuous deployment integration. If you think about software engineering 15, 20 years ago, nobody really cared about all these things. So we are today here with machine learning. And the continuous deployment is really important because it will help you to scale and make sure the quality is good, reduce the cycle time, and all those benefits. Version auditing, by following a workflow to put your artifacts in S3 in somewhere that eliminates human action of whether he or she wants to store the artifacts or not, because it's always there. And the last part, this is something that we observed in how people work together, because there are data scientists have different roles, engineers have their roles, writing some code for production systems, and then there are data engineers. How do you make them work together well? When you have a model that's done by data scientists, they have to talk to the client systems that please put my model in. Please find some time to deploy it, copy it over, or do something. And this is an expensive process because the client teams maybe have their own deliverable. They have their sprints. So to prioritize that, it will come another 2 weeks, 4 weeks after. So this iteration going back and forth is really slow because it's manual. By building something like this, like MDLC, you establish a strong contract between your teams so that your client teams will look at your output, the machine learning scientists, their result into maybe an S3 bucket or as a SageMaker endpoint, and just directly consume that. And then what happened behind the scene, training, updating, redeploying, those are completely managed by your data scientists. So it establishes really good boundaries across the teams. And frankly speaking, the way that all these teams work together on the machine learning, we're still at a quite young stage. And we really need to figure out what's the best way of having people working together efficiently and while also making sure they have a career development. So those are all the benefits that we mentioned. And if there's some more information where to learn more, then I'll pass it to Kunal. Thank you very much.
Oops. Thanks, Fei. So the learning journey doesn't have to end over here. We have a bunch of other resources for you guys to learn at home as well. And let me just share some of those with you right now. The first is the Machine Learning University. You can go to that link over here, and it's a great resource to learn a lot about what you heard here today. It has over 65 hours of video, 50 different courses. And the great thing about this website is you can choose the path you want. You can state whether you're a developer, whether you're a data scientist, whether you're a business decision maker, and it'll choose the correct course path for you to learn more. Or you can just access all of the videos. So definitely recommend checking out the Machine Learning University. The second resource is to go to aws.amazon.com/training. Another really great resource to learn more about building IT infrastructure on AWS. So obviously this talk, there's a lot of ML, and the previous one was a lot of those ML resources. This is more about AWS as well, more about step functions, some of the other resources you heard here today. A combination of both of these is a great resource to learn more. And then last, it's the end of the presentation. If you do have questions, meet us on the side or one of the sides over here, and we're happy to answer any of the questions you might have. Thanks, everyone.